In this video, we'll talk about solving second-order constant coefficient linear equations. So we're going to start by focusing on the simplest of all types of equations we can look at when we're looking at second-order equations, and that is ones that are linear, constant coefficient, and homogeneous. So to see where we're going to head with this, let's start back and looking at what this would look like for a first-order equation. We'll look at what is a first-order linear, constant coefficient, homogeneous equation. What does that look like? Well, that's going to be dy dt plus some constant a times y equals 0. Because we have first order, we have constant coefficient, so this here cannot depend on t at all. And this is just homogeneous, so the 0 on this side. But we know how to solve these, right? If we solve this, we can move the ay to the other side. We'll get that y prime equals minus ay. And then it's separable, and I will get the solution being y of t is c e to the minus at. The key point is that our solutions are exponentials. And what does that work? Well, if I look back to my equation here, the point is with exponentials, derivatives sort of keep the function the same. Right? If I differentiate an exponential, I just get the same exponential back with a constant in front of it. So this works because exponential functions are repeated or show back up when they're differentiated. And since that doesn't matter if we're doing one or two or more derivatives, this might be a good place to start to look for solutions to second order equations. Where does that lead us? What we're going to do, at least for now, is we're going to hope that we can find a solution of the form e to the rt for some value of r. We're going to assume this is a solution, plug it in, and then see what r has to be. So plug this in, what r should be. This will give rise to what's called the characteristic equation for this differential equation. The resulting equation for r is called the characteristic equation for this differential equation. So solving that equation, we get our values of r, which will give us solutions of the form e to the rt. Let's see what this looks like. What values of r is e to the rt solution to y double prime minus 4y prime minus 5y equals 0? We're going to plug in e to the rt and see what happens. So if I take my y of t to be e to the rt, then the first derivative is just r e to the rt, and the second derivative is r squared e to the rt. So I can take those and plug them in, and if I do, that will give me r squared e to the rt minus 4r e to the rt minus 5 e to the rt equals 0, or factoring e to the rt out, e to the rt times r squared minus 4r minus 5 equals 0. Now, e to the rt is never 0. So I can get rid of that. That's never going to contribute any factors here. The only thing I care about is this quadratic in here. So this quadratic factors as r minus 5, r plus 1 equals 0. So this means that r equals 5 and r equals minus 1 give solutions. This means that e to the 5t and e to the minus t both solve this differential equation. And that can be verified by just plugging those back into the original equation and seeing that it works out and gives us 0. So that's going to be our approach to solving these equations, at least at first. We'll have some more theory to back up why this works and sort of why me finding these two solutions here is enough to do everything that I want with these sorts of problems. Right? At this point, I've just showed you here are some solutions. We'll have ways to justify eventually that this is sufficient, and then really any solution that I want to find I can get out of these two because of things like uniqueness of solutions, where if I find any solution, I can build one that I want. I get the exact one because there's only one solution to this problem. So we'll build up the technique around this over the next couple sections, but as of now, we can use this method to try to hunt for certain special solutions of these constant coefficient and homogeneous equations, and then try to build them later to deal with things like initial value problems.